good news to me, we don't have an exam. It's not that good. So that's the bad news, right? But here's the good news. I have decided to set the paper in a scientific manner. Right? That's also bad news. But here's the thing. This time, the questioning is different. Again, but the good news is, you answer just what I asked for. Now there's a question. I give you a circuit and ask you to mark the supernode. That's it. Don't try to be very smart and write the equations also, do all kinds of things. I say, my God, I have already done the first question. Just a supernode. I give you the circuit, supernode. Photosynthesis, supernode. There are some things I have asked you to mark the minimum number of nodes. Just take the red pen, mark them as 1, 2, 3, 4, done. Right? That's what you know. There are only 2 complete problems. Complete means start to end. Write the things, mesh equation, this, that. All the others are just. There is one question here I have asked you for your, I guess, opinion on whether the current division can be applied. So the answer to that is yes or no. Don't write yes, I think it is this one. Not necessary. Just yes or no. Right? So there are about 11 to 12 questions specifically done in a scientific manner so that your outcomes can be checked. Everybody now talks about outcomes. Sometimes we give papers that are way harder than what is supposed to be. This time it's not. Right? So it's very easy, but really look carefully when you do the questions. Then there are 2. I saw your student feedback. Right? I saw your student feedback. And I was a little upset. Because there was 25% of your students who was marked saying basically the course outline was not given to you. What are we supposed to do? What am I supposed to do? Bring the course outline, drummers, dancing. Here's the course outline. So that thing is on the web page. So then I know that you have not paid any attention when you feel that feedback. Which is not good enough. Right? And I am looking to see what goes on in there. You just put 1, 2, 3, 4, 5. Don't do that. 25%, not a small number. 25% of it, I never gave you the course outline. I'm sure you didn't read the question. Course, answer your question. So please make sure you look at this properly. Everybody wanted me to do extra problems. I also know this one. Right? But I'm not going to do all the problems that you are having all the time to fix all the problems so that you see all the angles. Not going to happen. Right? Everybody else says that this is harder than any other courses. It should be wrong. No, there are other harder courses. You look at sustainability. Right? This is sustainable. Right? Not over. Right? So anyway, the exam paper is not too hard. If you looked at the course outline, there are 2 outcomes that I should be checking in the in this, I guess, midterm. Right? LO, right? 1, LO2. Right? Now go look at that. If you know LO1, you are thinking LO1. Huh? You can get 75% marks in the paper. So I have made sure that the question paper has 75% marks allocated to LO1. And then LO2 is the 25%. Right? So that's up to you to figure out which ones to do. And I am going to upload also my scientific sheet with all of the grades and marks, which of course doesn't have the question. Right? You can see how I have set it up. And this is the scientific way of preparing question papers. In the future, you are going to have almost all of us doing that technique to set question papers. So you can be sure that year after year, the question paper would be also of the same standard. I am going to first answer the questions that were SMS to me, email to me, WhatsApp, Viber and all that stuff. I am going to answer that first. In case I haven't answered your question, please write it in a piece of paper and then push it forward. Right? Because now here it's a big question. No? You can't stand up and explain. So put it in a piece of paper, send it up, I will answer. Right? So let me answer the questions that were asked from me previous. Now this was, I think, taken from a midterm somewhere, because I can recall this particular problem. This was a midterm exam question. But also, when you set a paper scientifically, each and every part of what I taught is in the paper. Right? Each and every part. Little questions spanning the entire stuff that I taught. So here you are. I think this was from 2013 paper, I think. Right? This is R1. 5.6 kilo ohms, R3 2.2 kilo ohms, R2 which is 3.3 kilo ohms, plus minus E2 equals 30 volts, E1 equals 20 volts. I don't know, maybe this should have been E1, right? Oh, there's a very hot question also. I don't know, maybe this was would have been E1, right? I have written it wrong. Okay, let's put something like 20 volts, I don't know. E2 is equal to 10. I don't know, I haven't got these numbers with me, right? Okay, so then I think the question asked you to convert this using the source transformation. Right? You were asked to change this using source transformation into a single current source with the resistor in parallel. That's what was asked. Right? So you got 3 arms. Each one has a voltage source and resistor. I should be able to convert this into a simple current source. Let's look at the rule. Here is what the rule says. Now, if this was E, right, this was R. If this was E and this was R, if I want to find out the equivalent resistance, and I also said this was called the Norton's theorem. Remember the Norton's? So how did I get it? I just said that you have to, in fact, look through this A and B terminal to find the equivalent impedance or equivalent resistance. How do I do that? I mean, the way I would do that is by placing this with a short circuit. Okay, so because I want to replace it with its internal resistance, so if it is actually a voltage source, you have to, right, replace it with a short circuit. So this is what I did. I took it out and replaced it with a short circuit. Then I look in through this to find the equivalent impedance of that Norton circuit. So I look at that, I find out that that's equal to R. Right? That's the first step. Then, because I want to convert this into a current source, what I have to do is to take the short circuit through A and B, right? What would be the short circuit current that is going to flow?
short circuit current. So if I mark it that way, right? If I mark it that way, this goes through this one, goes up. So if it goes up, this voltage has to go down, right? See, same current has to go through this cycling, right? So if it goes through this over there in the clockwise direction, the voltage drop is in the opposite direction. Here, this is plus minus, the voltage is going up. Now I apply either the Ohm's law, Kirchhoff law, whatever the law you want to apply. You have E going up. This is like what? Minus of I short circuit into R is equal to 0. So you have I short circuit being equal to E over R. Okay, E over R. So now I have to make sure this current goes through. If I have put a short circuit, that amount of current, it should go through A and B. Start from A, go to B. That's what I have to do. So I have to now draw the equivalence. I remember I explained this very clearly some time back. So essentially what I would do is, first of all, add another page to this page after. Yes, I would do what? I would take the current source. I don't know, I guess, which way it has to go, right? Which way it has to go, I don't know. This I know for sure is R, right? This way I know it. If I put a short circuit here, I should have I short circuit traveling through that. If I put a short circuit here, that R is going to be shorted out. So if the current goes up, that's how it comes. Right? Current goes up, goes down this way. There you are. So that is the equivalent circuit where this is E over R and that is R. Right? So if you have a voltage source this way, that's the R. This is how the current source has to be. So there you are. Now you know how to do this. Now I can twist and turn and the voltage source can be put anywhere. Done. Because why? We know how to do this. That rule is what is necessary. Right? Now if I ask you, okay fine, I want to find out if I have a resistor here that is opposite to this. This is E, that is R. Now what is the equivalent circuit? Norton equivalent circuit. You don't even have to ask anybody. That's what you would put. E over R, R. Right? Well, if you don't want to do all of that stuff, remember this. I would ask you not to, because why? Then you will have such pieces of information, tons of those information to keep in your mind. But here is the rule. Yeah, if you think you can't keep it in mind, write it in that piece of paper that you're going to bring into the class, and that's fine. I think you shouldn't, but if you want to. There you go. Is that okay? Fine. Now let's go back to the problem. Here, this is the problem. Control C, Control V. Now immediately you have no problem with this, because why? This can be immediately replaced with base E1 over R1, right? And it will have a resistance in parallel with it called R1. That's fine. You got the other leg now. You got the other leg. Again, this can be replaced by a parallel combination. Now again realize this is going opposite with a current source of E2 over R. Let's put this R2, right? Let's call this R3. Right? So E2 over R3 with a resistance in parallel called R2. Right? And then over here you have a current source that is going up. Let's call this E3. E3 over R3 and a resistance of R3. So tell me, up to this point, everybody okay?
Yes, everybody okay? No, you're not okay. Not okay. Do you understand? This is the time to ask a question. For this class, it's okay for you to talk. Yeah? Oh, yes, this is there you are. See, now you're picking it up. The moment you come to a like a, I guess level where you can fix my errors. Oh, sorry. Now this one goes up, this one goes down. You know, that's how they give a person, right? This is how they give a person a PhD. That's the rule. PhD, you start fixing the supervisor's errors, he wants to get rid of it. Which means you know what that particular subject more than him. Then he knows you are ready to be given the PhD. If you are there, you are going to isolate. Better to give the degree and let you go. Actually, that's all. Everything okay here? Yeah, you are not happy. I guess you are not happy. What is it? You. What's the problem? No, you are not. What's the problem? You are not happy. You can. That's the next stage. Absolutely, you can have that. Because there's a rule saying what? There's a rule saying if they are in a parallel, those branches can move here and there. Sure. Right. That's exactly what you're going to do. There's a rule saying that these branches can be moved any way you want. So I will move this like that. This going up, this going down, this going up, right? And then I will add all of the three resistors at the end. R1, R2, R3. This is E, right? 1 over R1, E2 over R2, E3 over R3. So this would be equivalent to now. Immediately now, I don't have to look at anybody else. I can rewrite this as a one resistor. Let's say let's say EQ, right? And then say capital I EQ. Another page maybe. They should have that also on this bar. Page after. Right? Now immediately you know I EQ is what? EQ is E1 over R1, right? Minus E2 over R2 because it's going in the opposite direction, plus E3 over R3, and REQ is R1 parallel with R2 with parallel with R3. Is that okay? That's the one that was taken from an exam. I remember this is something. I think it was taken from a midterm exam. Everybody okay with this? Yeah, okay. Good. Now, definitely in your midterm examination paper, there are source transformations. Not in this form, right? But in some form. Then the second question somebody had was also, I think, taken from that same like midterm exam. Folks, if you want me to stop and explain, please indicate, right? Otherwise, I will keep moving. Here. Right? This is plus 16 volts. This is 2.2 kilo ohms. This is equal to 5.6 K. This is 8 milliampere. That was R. And the question was that I think the exercise had two parts. The first part was to find the Thevenin equivalent circuit across this, right? Basically, this was the one that was taken as the RL. So you have to remove it from the Thevenin circuit. And second is you are supposed to identify the R for maximum power transfer.
right? Maximum power transfer. So now let's go back and look at it. If you ever see a circuit with things hanging out, I have asked you to do what? Redraw the circuit that makes sense to you using batteries, voltage sources, passive elements, I don't care what. Right? You have to do that. So now here, we understand this, we understand this, we understand this, we understand that, but that one is hanging out as a 16 volt. Now we get to redraw the circuit. So here is how we are going to redraw the circuit. There would be a ground somewhere here. Right? You have a resistor here. You have a resistor here. Voltage source here. 16 volts. 2.2 kilo ohms. 5.6 kilo ohms. 8 milliampere RL. There you are. Now it looks like something we can handle. Something we can handle. Now, if there is milliampere and K, go check the units. If the resistances are in kilo, then basically the voltage is in dB, the current would be in milliampere. So all of the units are perfectly okay. Now what we have to do is to go through the steps of finding the Thevenin equivalent circuit. What are the steps? You have to eliminate the load resistor. First thing. Then through that little hole that you are creating, look into it and find the equivalent resistance. How do I do that? By replacing all the sources with their internal impedance. So if it is a voltage source, I have shown you have to replace it with a short circuit. If it is a current source, you have to open circuit. That's it. Now let's try to solve the problem. I'm adding too many pages, right? New page after, okay. There you are. So you got this circuitry. Now what we have to do is to draw the equivalent circuit that we are going to use to find the open circuit voltage. How do I do that? This is open. There you are. That is the current source. This is the resistor. Other resistor. Voltage source. We have to look through this. You want to call this A or B, that's fine. AB. Now we got to find the R of TH. So how do I do that? I have to place this with an open circuit, that with a short circuit. This was 5.6 kilo 6 kilo ohms. This is 2.2 kilo ohms. So if I start to do that, I would have a resistor like this, which is 5.6K, and when I put a short circuit here, this comes in parallel with that, which is 2.2 kilo ohms, and this is A and that is B. Then immediately we can figure out R of TH is equal to 5.6 kilo ohms in parallel with 2.2 kilo ohms. So you want to find the exact number, you would write 5.6 times 2.2 over 5.6 plus 2.2, right? So how much that is, you will get the value. That's the first stage. Now we got to find the open circuit voltage. How do we find the open circuit voltage? What would be the best method to use here? Open circuit voltage. Which one would you use? Because I haven't asked you, in that question I haven't stated which method you should be using. Or maybe I did, right? I think I asked you to do nodal analysis. Yeah? Yes, which one would you use? Nodal. Usually when I ask you to do it in a certain manner, that will be the most difficult one.
You can use mesh if you want, right? One of the sources known already, the currents. If you use mesh, you have another stage to find the V. Use node, right? It will give you the value already. So if you are going to use nodal analysis on this, I will let me draw. So you realize if I put here a node, right? If I put here a node, right? That node voltage is this open circuit voltage. So you got V open circuit is equal to V1. See, if I can identify V1, my problem is solved. So I would draw the circuit again, draw the circuit as much as you want, but I think I will ask you to actually answer in the examination paper itself. So I will give you adequate space, but not a lot of space. So they will give you some other sheets, right? Rough work sheets. You can draw the circuit as much as you want, but in that you only give the answer. Here you will have a resistance, you will have a voltage source here, current. Don't put a node here, because why? We have told this with that is a single branch that we have seen before. Right? I said if I have a situation like that, use it as a one single branch. Don't put a node there and then create yourself a super node, all kinds of nonsense. Right? Just use it with a resistor and a source is a generally considered to be a single unit. So I have a node here. I will call that node 1, and now I start to write down my equations. 5.6, 2.2, this was 16 volts, that was 8 milliamperes. Right? So if this is my node, that would be my surface that I am going to use for the Kirchhoff current law. Then I will write the KCL for node 1. You know something? Every year when I get feedback, there is a single student every year, right? Every year in the feedback form, he will write C, and current. Right? Every year there is one person. So at least I know that person is listening, at least to what, he's not listening to what I'm saying. At least how I'm saying it, he's listening. Yeah? I know he was the first, I've been joking, but it's fine, right? Right, so you apply the Kirchhoff law here to this node 1, the surface. I am taking everything that is going out of the surface to be greater than 0. So this is 8. I'm going to drop milliampere because why? I have already checked all these things, units. I know this is going to be in terms of volts. I already checked it, so there's no problem there. This is 8 plus here I'm going to take V1, take away 0. Of course, we understand this whole thing is also a node. Right? This whole thing is also a node. If you want to mark it, that's fine. Over 5.6, because it is in milliamperes, this in K, I have dropped the units because they all match. Plus, I have V1, take away 16, V1, take away this voltage, which is 16 over 2.2 is equal to 0. Now immediately I can find V1. So how much is V1? V1 is equal to 16 over 2.2, right? 16 over 2.2 and minus 8, right? Minus 8, 16 over 2.2 minus 8 over 1 over 5.6 plus 1 over 2.2. How much is this? So this is about, so you have to get the actual value, because if you approximate this to 2, it's 0.
I think I got an answer something like 0.019, yes, minus 0.019 milliampere. I don't know. Can somebody calculate this quickly? So this is 16 over 2.2, right, minus 8. So it's minus something, right? So you have answer over did you find it out? No. Minus 1.15. Minus 1.15 milliampere. Sorry, volts. Right? Minus volt. Now remember, this I don't care whether this is positive or right negative. If it comes out to be negative, then I know that the open circuit voltage is in the reverse direction. Right? So I have taken VA to be greater than VB. It so happens that VB is greater than VA. Right? So if I want to now draw the equivalent circuit, you have a R. How much was the resistance? How much was this? 1.57 K. Right? 1.57 kilo ohms. 1.57 kilo ohms. And can you tell me which way am I going to? So that's going to be R. This is going to be A and B. Can you tell me which way am I going to put this battery? Okay, you have the battery. There are 2 points. One is the top part, which is along the line, is going to be positive, and the shorter line is negative. Right? So, longer line is down. There you go. Longer line is down, and it will be 1.15 volts. That's it. Right? Now the second question is, they ask you to identify R for maximum power transfer. We have already shown that R should be equal to the equivalent resistance. So R should be equal to 1.57 kilo ohms for you to have a maximum power being transferred. Is that okay? Right? This is fine. Okay. Question number 3. Is there anything I can answer here for you, or are you all okay? All okay, yeah? Here is another question that somebody asked. Right? There was another question that was sent by somebody. It had a resistance and a current source like this, and it had a this was RL, was 9 ohms, this was R1 equal to 5, this was equal to 10, and R2 was equal to 4 ohms. And in this they asked you to, so they have highlighted they have highlighted this box. Right? They have highlighted this box and then ask you to actually replace this with its Norton equivalent. Norton equivalent circuit. Right? So how do I do this? If I want to replace this with its Norton equivalent circuit, what would I do? Yes? So this Norton equivalent circuit theorem says that any network with independent or dependent sources, remember we are not asking any questions in like dependent sources, because for this course I have dropped dependent sources. But because I wanted you to see a little bit of it, so I taught you some questions and I'm going to do some questions of it maybe later. I already did one or two. I guess next year when you do a course, electrical circuits or something like that, they will teach the same set with dependent sources. Slight changes, right? So if you understand this, you can understand it next year. Or you can understand this next year too. Right? So if it is this not an equivalent circuit, what it says in the system is that any network of sources and whatever the stuff can be equated to a single current source in parallel with a resistor. That's what it says. And this current source should be the short circuit current that is going to appear across the loop. Right? Those are the rules. Okay? So let's start. That's all you need to know. Then what you do is you go about doing it the regular way. You take out the load, draw the equivalent circuit, look through that little hole that you're creating, you actually replace all the sources with their internal impedances, find the equivalent impedance or maybe the resistance in this case, then you find the short circuit current. End of story. Right? So let's look at it. So the very first thing you're going to do is take out the load. Remember, load can be even half of your circuit. I'm going to do a problem like that. Now, all this time you are thinking load is just a resistor. Not, you can take half of the circuit as the load, which means take everything out from that side and then whatever you have after that, you can find an equivalent circuit. So here it is just this particular resistor. We call it A and B. Then you are going to take off this load and leave only the current source and the two resistors A and B. R1 10 milliampere. Let me just put this as 5. Now remember, again, if there is some milliampere in the system, check to see whether all units match. So here this is in basically these amperes, right? These amperes, this is in ohms, fine. Which means voltages will be volts. No problem. This is 4 ohms. You have to look through that to find the equivalent impedance. If I do that, all sources have to be replaced by their internal impedances. So I had to redraw this by placing this which is internal impedance, which means an open circuit. So if I take an open circuit, this goes through that. So you have a resistance A, B, look through RTH. This is 5 ohms. This is 4 ohms, which means R of TH is equal to 4 ohms plus 5 ohms, which is equal to 9 ohms. Right? Is that okay? Okay. So that's okay. Right? Equivalent resistance. Now we got to find, since it is this Norton's theorem that we are going to apply to it, and again you need to find across AB, you apply a short circuit and find out what is the short circuit current that is flowing through AB. So there you go. You now have the rule. You have to now apply it to the system. So here you are. You have a resistor. You have a resistor. You have a current source. Here you apply a short circuit. That is I short circuit. Right? I short circuit. This is equal to 4 ohms. That is equal to 5 ohms. This is equal to 10 amperes. Now this circuit looks a little messy. We don't want to do all of these things. So what do? We redraw the circuit to make it look nicer. Yeah? You don't have to. You can just identify. You can do that. So if I drag that point A down here and connect it to this, I get a nicer looking circuit. So I have this resistor, I have that current source, I have that resistor. See, I drag this point because all these points are the same. See, this point, all this is the same. See? I repeat out. This is what I get. Does that make sense? Then, what passes out from here is I short circuit. The old way we had to now do, we're dragging I short circuit. In your head you do this, right? In the class you don't do it in the exam. There are problems like this in the exam. So, now all of a sudden you are paying attention. All this time you are going, Norton. This is 10 amperes and this is what? 5 ohms. Now what do we do? How am I going to find I short circuit? Doing what? Okay, we don't like this. It will be not like this, and if you wanted to make it nicer, but at an examination, don't make it nicer, more nicer, better, right? Just stick to in your head, clean it up and draw it. Otherwise, you'll be having pages and pages of nicer looking circuits, but the question is not answered, right? I can have it like this. Right? This is 4 ohms, that is 5 ohms. This is equal to 10 amperes, and I short circuit is the same thing that is going through the 4 ohms. Why? If the branches are in parallel, I can swap them around as long as I don't have anything up here. Right? If I have anything up here, you can't switch. Nothing up there means all those points are together, so these branches can be rotated to any place I want. Now how do I do it? Yes. Current division. So immediately I short circuit is going to be what? 5 times 10 over 4 plus 5. And you got your answer. Right? There you go. Now you got to make sure you draw the circuit properly so that the I short circuit will appear across the same place. So what I would do is the current goes I short circuit. That is the equivalent resistance, and that is A and B. This is the 9 ohms. So this, how much was this? 9 ohms. That's 9 ohms. And this would be like 9, some wacky amount, right? So I don't know what that amount is, right? There you are. Equivalence. So you can. I think they asked you a question here. They are asking to see whether this one, which looks messy, it is not messy actually, really. This is easy. That can be actually, right, replaced by that. Sure. But make sure that I have allowed you to do that. If I say not do, you think, this guy, no, this is easier. Don't do that, because if I am going to give you a question, I am not testing on that. Right? So you can't change things. If I don't indicate anything, you can use any method you want, which is easier for you. Sure, you can do it. Right? Sure, you can do it. No problem. Okay. Is that okay? There is another question. I am not going to do this, but I am going to show you how it's done. Because why? Again, this is finding equivalent circuits. Right? Actually, there were about 10%, 10 to 15%. I should give you that. I will upload what your feedback said. Right? Because I think students need to know this. You know how, as an individual, you are thinking, this guy is too fast. Right? But then if you take the whole class, there were about 15 to 20% of the people only who said I was fast. There was no indication that it was slow. I'm almost sure it's not slow. Right? 15% of them said it's fast. So, if I don't slow down, it's because almost 85% of you think it's okay. The other 15% need to work hard. Right? Maybe come to me or ask for extra help or whatever you necessarily get with them. I will help you. Right? No problem. I will upload. That's good, right? You will never get to see those feedbacks. Right? I will upload that this time. No, when I go back, I'll upload it. Right? Because, I'll tell you why. Not because I kind of like you guys. It's because when the people come to do accreditation, they are going to ask you, how was the feedback? Did you give feedback? You say yes. Except for that 20% who said no outline. Right? Then they are going to ask you, did you know, or did this lecturer come and talk to you regarding the feedback? Then you are going to say no. Now you can't say no. I'll upload it there, you look at it. Oh, it's wonderful, and you move on. Right? Then you can't say no. Then I can say, oh, yeah, it's there. They didn't look at it. Yeah, so I'll put it up there. Good. Now, here's the question. This, I will not ask you a question like this, but this is very nice. Right? Got it? That was the question. This was E and then this was RL. This was R1, R2. I think in this. Oh, hold it. I can remember the question for this. Okay. Here, I think when they asked me the question, they asked me why was I short circuit, which was, I think in the book it was called IN. Okay, I can now remember. It was called IN. The question was like, why was this one IN equal to the current that is passing through the 4 ohms? Now you can see, no, right? See, this IN is the one that passes through 4. Yeah. You have an earth here, still you can't have current going to earth, and then other side nothing. Poof, gone. You have a neutral point, but the current goes in and comes out, right? Doesn't go in and then go to a black hole, no. Other side, no current. So there was current, there's no current, then there's no current this way also. Then there's no current in the entire circuit. You can't have that, no. Though you have the ground, it's only for the voltage. But basically the current is going through the loop, right? So okay, that was the question, right? So this current is the 4 ohms current, right? Occasionally I remember some of those things, right? R1, R2, let's say this was R3 and R4. Now, they had asked you to solve this and find the equivalent circuit, the Thevenin equivalent circuit to this. That's the load. Right? Now, all this time, you are having loads, vertical loads. So when you put horizontal, you are like, what happened? Now this horizontal. Now you are twisting your head like this. Let's see how this is going to match. That was your problem. Don't worry. Put plus minus the way you feel is good. Right? Put the plus minus, but when you write down the equation, you make sure that the plus and minus that you use is the one that ends up in the equation. Remember, in the second lecture, I told you, you can have the same one, but you can have basically the current being like marked up. Then what happens is when you put it to the equation, it turns out a minus, which means it should have actually gone in the opposite direction. Here, the same thing, right? So, this is RL. So, essentially what you would have done was to take this circuit, Control C, Control V, let's bring it down here, right? Then, you take this out, this is the load, this is AB, I don't know, I can take it any way I want, I can take this to be plus, that to be minus. If I take it like that, this voltage V open circuit goes that way. If you did not want that, you would have taken, I guess, that had to be like negative, this to be plus, then your V open circuit would have gone that way. So once you put that, when you put down the algebraic addition, you put the proper, I guess, right, the direction of the arrow, and your equation would come out perfectly. Don't worry. Now, if you are unable to solve the problem using this triangular stuff, pull it open. Pull the circuit open. Here, if I do that, essentially the circuit, now if I take this point and I drag it out, it will look like this. Right? This is A, this is B, and on the other side, that's what you got. This is R1, R2, R3, and R4. See? That's it. See, these 2 points are the same here. Now you analyze this circuit using regular laws. For example, here, I can apply what? Tell me, it's a good exercise. I'll give you 2 minutes. Find me a technique of finding VA. Because if I know VA, if I know VB, I can find VA. Because then VA, right, minus VB is VA. Tell me the technique. Quickly, put it down, write it down. Just put it in terms of R1, R2 and E. Okay, I put voltage of E. So this is all about taking a look at the circuit and immediately clicking, saying, oh, that's the easiest way to do it. So how would you do it? If I ask you to find this, find the open circuit, voltage. No, so hold on. Before that, if I want to find the equivalent impedance, what would I do? If I want to find the equivalent impedance here, right? If I want to find the equivalent impedance here, I would have done what? Place a short circuit here. The moment I place a short circuit here, R1 becomes in parallel with R4, R2 becomes in parallel with R3. See, I'm hooking up this point. So you take the circuit and actually fold it down. Did the mic go bust? Yes, it did. Okay, you do it, I will call up and get this. කවදා මේක වෙන්නේ. I was shouting so much that more battery power is being wasted. So, how would you do it? Mesh analysis. But how would you do it? Huh? How would you do it? What do you do? How would you do that? Very simple, right? You have to be very quiet. I can't shout. Here, very simple, right? This place is open, right? So, if it is open, I can redraw this as that, right? This voltage will appear across these two, so I can use voltage division. Here also the same voltage. So if I look at A, it will be E base into R4 over R1 plus R4. And on the other side, if I look at B, VB, again I realize it is E times R3 and R2 plus R3. Right? So now if I want now remember you have chosen that to be plus, this to be minus. I'll use blue. This to be plus, this to be minus. Immediately you will do what? VA, right? Minus VB is what you're going to use. That will be what? VA is E R4 over R, right, 1 plus R4 and minus E R3 over R2 plus R3. But if you had chosen the other way around, you would get what? You would have chosen VB, right, minus VA. Because why? VB is now taken to be greater than. Okay, thank you. You have taken V, right, B to be greater than VA. So your equation is what? ER3 over R2 plus R3, right, minus ER4 over R1 plus R4. Right? One is the minus of the other. Right? One is minus of the other. So that's how you solve that problem. Right? Okay, okay. Do you have any other question that I can answer before I go on to my tutorial problems? No? Okay. Good. Tutorial problem 1. So I'm starting from the other end and we'll walk back. Right? I start from what I did at the end and then walk to AC and then finally if I have time we'll go to AC. So how do I do this problem? that better? First of all, tell me.
This is a question taken out of the e-book, but in the book the question number is slightly different. Right? So look at the problems I gave you just here. How do you do this? The part 1 is finding average power which is delivered to each of the elements. How do you find the average power delivered to each element? Average power means they are asking for the active power. The average power is the active power. Right? Active power. What is the active power that is going to be? First of all, if you want to find an average or reactive or any other power, you need to know the B and I. Right? B that is across that element, and I that flows through the element. Tell me what is the current that is going to flow through R. Also remember, ladies and gentlemen, at the examination, some questions I have done it partially. For example, if a question like this comes, if I don't want you to go through node to the analysis, all kinds of rubbish to get this IS, I would have said this in this circuit IS is this. Of course, you could have done it too, but I have also calculated the IS, right? But I sometimes give you because I don't want you to spend your time in doing that. Then assume. Don't try to check whether my answer is correct. Right? Whatever the answer I give, use that to do the other part of the question. Right? So this time is going to be something very, very different from the papers that you have seen that's on the net. Right? And also, there are two engineering programs that we have offered. One is from SHU, Sheffield Hallam University in the UK, and the other one is the Australian one, which is offered by the Harvard University. They are two different exam papers. So you go to the library and say, give me the first year. They are going to photocopy the first year of the SHU program and the first year of your UGC program. So some people ask me questions like, when you photograph of program, some other type of question which is done to the SHU program. Nothing to do with you. Right? Remember, if it's BH, then it's SHU program. If it's BSc, that's your program. How do we do this?
Now here, don't have to spend much time. You realize this voltage, right? This voltage is the one that goes across all of these things, right? All of these. So if this was IR, if this was IC, and if that was IL, you can immediately say that IR is equal to E over R. Right? Now since this is an AC circuit, this is a capacitor, I have to put the impedance here. That will be like what? Minus J of 5. Here I have to put the impedance. J of 4. Because this is an inductor. Here this is just 2. Right? There you are. Then if I want to find IC, that's going to be what? E over, okay, let me put the actual values, that will be easy, 20 volts with an angle of 0 degrees over 2 is this one. Here, this is 20 volts with an angle of 0 degrees. Here, it is actually what? Equal to 5 with an angle of minus 90, right? See? Because why? Minus J5 is equal to that. Correct? Okay. Then I want to find IL. That's going to be 20 volts with an angle of 0 over 4 with an angle of 90. Right? So now I can write this. This is equal to 10 amperes with an angle of 0. Here, this is equal to 4 amperes with an angle of 90. Right? Here, I can write this as equal to 5 amperes with an angle of minus 90. So, IL, IR and IC found. Right? Now, VI will give you whatever you are asking. Now, tell me, what is the average? Now, when you say average power, that they are really talking about the active power. So, tell me the active power that is going to go through the 2 ohm resistance. Yes, what is the active power? It's I squared. So I is what? 2 that equal to 10. 100 times 2. 200 watts. Right? Active power. Average power delivered. What is the average power that is going to be delivered across the capacitor? Yes, what? Really? What is it? Can someone say on this side? Yes, what is it? Anybody? Yes, what is it? No. No clue. How about you? No clue. Zero. Because why? The capacitor does not have a resistive component. Only I told you last time also, only the resistive component will dissipate active power, which is measured in watts. No active power. So, 0 watts. How about the inductor? 0 watts. Okay? Right. Part B. The same argument applies for reactive power. There is no, right? No, what? Reactance in a resistance. If you are going to dissipate reactive signal power, it is I squared into X. Right? X is what? X is the reactive part which comes from the what? Comes from which part? The imaginary part. Right? Resistances do not have an imaginary part. So it cannot dissipate reactive signal power. So if I take a resistor, for part B, the answer is 0 VAR. No, 0 watts. Watts. Because why? That's how we measure the reactive power. 0 watts. But for the others, now you can. It is I squared X. How much is for the second one? For the capacitor, you have I equal to 4. So it is 4 times 4, 16 times X, which is 5. How much is it? 60 something? I don't know. Whatever, right? So there you go. For the other one, 4, you got 25 times 4. Right? Again, 100 watts. You can take your answer. That's what you should do. That's for part B. See how easy is it if you know the rules and the regulations and the stuff. Answering this is like that. Now, if somebody asks you that question at an examination, how long will it take to answer it? Half an hour? What 10 minutes? Few seconds if you know what you are doing. Right? So there you go. See what is the apparent signal power. What is the apparent signal power? P plus JQ. Right? So you want me to write it down? No. Maybe write it down here. Better, right? So when you go home, you are not so it's not recorded also. Okay. Let's put a page after this. Right? So for A, right, you have average. So you have P of R. Remember, active power is always represented using P. It's equal to, you have I squared of R, which is 10 squared of 2, 200 watts. Right? Then you have capital P of C, capacitor 0 watt. Right? Then you have capital PL, which is 0 watt. Okay? Then you have B. In section B, what they're asking for is for the basically the reactive power for each element. Right? So you will write capital QR. There is no reactive power for a resistance. Right? Capital Q of C is I squared, which is 4 squared into I squared X, which is going to be 5. 16, 5 is 80. Right? Then you have capital Q of L, which is going to be again I squared X, 5 to the power 2 times X, which is 4, I think. 4, and that is equal to 100 watts. Right? So you realize P is I squared R, whereas Q is I squared of X. Right? Now they ask you in part C, what is the, so they are asking S of R, which is apparent, right? Apparent power associated with R should be equal to PR plus J of capital QR, which is equal to PR, which is equal to 200 volt ampere. Because why? This is 0, right? Is 0. 200 comes from that. Then S of C is what? See, find apparent power for each element. S of C is capital P of C plus J times capital Q of C. That will give you J times 80. Usually, as a practice, we give you the mod value of this, right? Which will give you 80 volt ampere, right? 80 volt ampere. Then you have S of capital L, right? If you have a complete complex number, then you can state the complete complex number. If not, you give the magnitude usually, right? Here we have the P of L plus J times capital Q of L magnitude, which will give you J of 100 magnitude, which is equal to 100 volt ampere. Right? Part D. Now for part D, you are supposed to find it for the entire system. How will we do that? How will we do that? How can you find it for the entire system? Yes? Entire system? How would you find it for the entire system? If I take the whole system, I have E, which is 20 volts with the angle of 0, and then from the source I have IS going out. I already found out IS. IS is IR plus IC plus IL. Right? So we add them up. right? Part D is I of S is equal to I of R plus I of C plus I of L, which is equal to 10, 4, 5. Right? 10 with an angle of 0 plus 4 with an angle of 90 plus you got 5 with an angle of minus 90. Is that correct? 5 with an angle of minus 90. Right? So I have to extend this. How would I extend this? 10 plus, how much is this? J4, right? This is minus J5. That's going to be equal to 10 minus J. Right? So you have IS being equal to 10 squared plus 1 squared root with an angle of inverse tan of minus 1 over 10. Can you tell me what is this minus 1 over 10? Okay, I just want to highlight something. Hold on, right? I will just keep this problem a little bit. New page after. Right? I want to go back and do a little bit of complex numbers. Right? Here. So, we will take 4 different complex numbers. First one is 12 minus J12. Second one is 12 plus J12. Right? And the third one is like minus 12 plus J12. And the fourth one is minus 12 and minus J12. Can you tell me for all 4 of these what is the R theta form? Because if you get an angle which is greater than actually 0 and is less than 180, you will not have many problems. But when the angle goes more than 180, you have trouble in figuring out where the angle is. So, usual practice, if you are like not very sure, is to draw this complex number. Right? So, if I take 12, this is x is equal to 12 and j is minus 12. So, your complex number is over here. This is 12, that is minus j12. So, if I am going to put down this one, that is my basically angle. This is my angle. So if I want to put this down now here, I guess magnitude of 12 minus J12 is that. Right? Check it and see, right? I have got it as basically 70. Now this angle here, theta, is actually 45. 45. Right? 45. So I can put this down as 17 with an angle of minus 45. See? Minus 45. Or I can put this down as 17 with an angle going all this way from here to here. 270 plus 45 will give you 315. I can write it like this. But as a practice, you do not write it like this. You always want to ensure that this value is between 0 and 180. Right? Value is between 0 and 180. How about here? you realize this is 12, this is going to be the real axis, that is imaginary axis, J12 is somewhere here, that angle is now 45, right? That angle is now 45. So if I want to put this down, I would have 17 with an angle of 45. Oh, I could have also written it like this, right? 17, right, minus 315 degrees. Yeah? In the other way. How about this one? You realize this is minus 12, J12. That's where it is. Right? This one is going to be 45. How would I put that one? I would put that one as 17 with an angle of 135. Because why? That is 135. Right? Then I guess last one is, this is minus 12, this is minus 12J, sorry, J12, that's where you have it, and this is 45. So it will be 17 minus 135. Right? So please be a little bit conscious of this, little bit conscious of this when you write down what you have here. How much is that? And please remember, your calculators will always state an answer in terms of radians, right? In terms of the radians. So you have to multiply by 180 over 5 to get the actual angle. How much is this? 0.1. About 6 degrees, right? How much is this? Right? So now you have IS. Okay. We'll take a very short break. If you take a longer break, I have to stop the class at 4:30. Right? 1:30, 4:30, right? No, 4:30. Okay, go for a couple of minutes break and come.